Hi, I'm Larry Zitnick, a research scientist at Facebook AI Research, and thanks today for joining me on a discussion about evaluations. So the title of my talk today is the evaluation streetlight, and I'll get more into detail later about what that actually means. So when I say evaluation, I'm not just talking about evaluation metrics, because that's generally what we think about when we think about evaluations. But you also need to consider the training data set that's used to train our models, and then also the testing data set that we use to then run our evaluation metrics on. But before we actually get into what's being used today and some of my thoughts on limitations and what we should be thinking about, let's take a look back over the last, let's say, 10, 15 years, and let's look at the data sets and evaluation metrics that we used and try to understand better what implications that had on the research that we've been doing. So one place I'd like to start is Caltech 101 and 256. So this is one of the first kind of large-scale data sets that was out there. It had a lot of different categories, 101 or 256, as the name implies, and had a lot of, at least in that time, a lot of training data. But do you remember how much training data there was per category? Well, the experimental setup was to have either 15 or 30 training examples per category. Now think about that. You have 100 different categories and you have 15 examples per category. How does that limit the type of models that you can actually train? Well, if you think about it, it wasn't even that, like the type of mentality didn't even exist back then. It wasn't like training models. It was more about hand-coded feature design. So a lot of the work that went into this was not in learning new features, but it was actually how can I be clever about the features that I can hand design that I can then train, let's say, a linear classifier on top of to then do a good job of recognition. So that basically, that mentality of, hey, the way you create features is by designing them yourselves was kind of baked in to this data set. Now, of course, that's going to have some bad repercussions, like making certain people upset. And this had another implication, which was if you actually looked at the training data that's used, you'll see something that's kind of interesting here, which is this is one of the first data sets that had real images in it. Like these are obviously all real images. However, obviously there's some peculiarities about this. These aren't motorcycles like we might, normally see them in photographs. They're nice side shots, all facing the same direction. Some of them with white backgrounds. They had to make the data easier because of the assumptions made at test time. And also the algorithms that were available at that time, around 2005-ish. Now, after Caltech 101 and 256, the data set that really gained in popularity was PASCAL VSC. And this is for use for object detection and is actually still in use today. There's 20 different classes, had 30,000 different images. And the task was not image classification like Caltech 101 and 256, but it was actually object detection where you try to draw a bounding box around the different objects. Now, one of the interesting design choices in this one was the evaluation metric itself. So there's something called intersection over union, which is basically the intersection of two bounding boxes divided by their union. And you look at the ratio of that. The higher the ratio, the more accurate the predicted bounding box is. And if you look at different IOU metrics or different IOU amounts, you see here on the left is an IOU of 0.5 and what that looks like. And then on the right, you have an IOU of 0.9. Now let's say that you're somebody who actually wants to use an object detection algorithm. Which one of these thresholds do you think would be most useful? Do you think it would be 0.7, 0.9, 0.5? I mean, looking at this, for a lot of applications, maybe 0.7 you can get away with. 0.9 would be awesome. But 0.5, it's pretty loose. But what did they choose for PASCAL? Was it 0.7 or 0.9? No, it was 0.5. And why is that? Well, that's where the algorithms were at the day. If you would have done 0.7, all the results would have been really bad. So since the algorithms didn't do that well, they had to loosen the threshold, the IOU of 0.5, to actually see like gains and progress within the field. So that's something to keep in mind is that, and this isn't just PASCAL VSC, but it's a lot of other scenarios as well, where we set our threshold, we set our evaluation metrics, not based upon, what's going to be useful or practical, in some application, but it's where the research field is today and how can we effectively measure the progress given the state of the art as it currently stands. So then we fast forward to 2011, we have Caltech, we have, PASCAL VSC, and then you have somebody like Jeff Hinton, running around saying, I had this new thing, it's called neural networks, new, of course, new for the second or third time, maybe fourth time. And he was saying, how do I convince vision folks that DNNs work? And he goes to somebody like Jitendra, and Jitendra says, well, it's obvious. The coolest thing right now is PASCAL VOC. You should, show that you can do well in object detection. But then, Jeff is like, well, I can't use PASCAL VOC. There's not enough data. Even with 30,000 images, that wasn't enough data to train an effective neural network. So then Jitendra was like, well, all right, maybe use ImageNet. Nobody's really using it. As computer vision folks at the time, they're like, well, that's way too hard. No way we're ever going to be able to solve that. And is chipping the images. I mean, what do you can do with all those images anyway? And Jeff was like, oh, well, that's the right amount of images. Let me try it out. So, ImageNet, as we all know, it's the data set most people use is about 1 million images, 1,000 categories, and it's a classification task. And, this has been told many, many different times. This is what enabled the deep learning revolution within computer vision, because it's a data set that actually had enough data to train neural networks. And without that data set, then we wouldn't have been able to show as effectively that neural networks actually work. Now, one interesting design decision in ImageNet was the evaluation. And here, it's a classification problem, yet the classification, and when you think classification, you generally think, okay, each image is one of 1,000 categories. So what is the obvious thing to do? Well, it's top one, classification. So like, did you classify that image correctly? But one of the most popular metrics, especially in the beginning, was top 5, which is the ground truth classification label within the top 5? And this, unlike the PASCAL, which was the evaluation metric was driven by where the state of the art and algorithms were today, this choice was driven by the test set, the labeling of the test set, which is many images had multiple categories in them, but they weren't actually labeled. So it's possible that, if you gave 3 or 4 answers, that they were all correct if you had a human go and review them, but only one of them was known to be correct. So that's why the top 5 came about. So here, it's interesting that the evaluation metric was driven not by the state of the art, but driven by the flaws in the testing data itself. And it's really interesting. I've seen several papers come out recently on reevaluating ImageNet and adding more ground truth labels to it. And those are quite interesting results. And I encourage everybody to go out there and read those papers, because it really gives you some insight into where the field is right now and whether ImageNet still has more legs. And then we come to COCO. This is a project that I was actively involved in, along with obviously many others. And let me give you some insight into the different decisions that we had to make in generating this data set. Because in generating this, we had to really think about all 3 of those things I talked about in the beginning, which was evaluation metrics, training data, and testing data. So first is the data itself, the training and testing data. Up till this point, a lot of the images were captured by doing Google searches with different keywords, and they basically result in a lot of images like you see here on the left, which we call iconic images. It's like an object, it's kind of big in the image, the background's not too cluttered, that sort of thing. But what we wanted to do was move the field towards more complex scenes, more like real world scenes, like the ones on the right, where there's multiple objects in the scenes and much more complex, and it'd be just a harder problem. So we had to find a way to get those images that you see on the right. And that's one of the reasons why we chose Flickr. Generally, those images, look more, realistic. The next thing we had to decide was what categories. And this, you would think, it's not that hard, just come up, with 80 or 100 or 200 categories. This was tough. And we debated this for, I felt like months, Pietro and Serge and all them, we all had these different ideas of how to do it. But one thing was really clear, which was it wasn't trivial. So for instance, we thought about what are some everyday objects you have around the house? Let's just have them in the data set. And one of the ideas was hairdryer. And I think this category even made it into the ECCV paper that we published. But hairdryer never really got added to the data set. Why? Well, it's hard to find images of people using hairdryers because it's not a very flattering image. Finding 3,000 images of people blow drying their hair on the web is just not going to happen. So sometimes there's this bias when people take pictures of. And then you have another problem, such as cabinets. We had this for like buildings, cabinets, a lot of different objects where you look at the scene, like you segment it out, the stove, the microwave, the refrigerator, the sink, but how would you segment out the cabinets? Like, is each door a different cabinet, or is it like the part that's kind of put together at one time? If you had 2 different labelers, like label the cabinets, would they segment it in the same way? it's really ambiguous. These terms are ambiguous. So for this reason, there's certain categories such as cabinets that we didn't include, but it would make a lot of sense to if you're doing, a real world system or something like that. And just to kind of give you a sense for, how far along we are in the field, these are the top 100 nouns that currently exist. What do you think? How many of them can we actually recognize? We go through here, we can see people, yeah, we did that. Man, woman, we kind of grouped that together. Child, school, that'd be hard. Student, how do you know if somebody's a student or not? That's gonna be tough. A group, a part, a hand maybe. Labeling a weak in an image is gonna be tough. But if you look through all these different words, most of them are not in data sets today. Most of them are not being recognized. A lot of them have these ambiguities that we talked about. Something like a book is interesting too. Labeling every single book in a bookcase is tough. That's why we didn't have books in the data set. All right. Another question we had is like, do we want to stick with bounding boxes or do we want to do something, more complex? Do something more complex. And we tried to figure out for image segmentation, how do you do that in a cost-effective way? And that was really tough, but we decided that we wanted to push the field further by going into segmentation and not just doing bounding boxes. So we took the time, we took the money, it took us a while to develop the user interface to then create these image segmentations. And then finally, metric. So as we know, 0.5 is kind of driven by where the state of the art was, but we wanted to push the state of the art further. So we had a lot of discussion about, do we do 0.7, do we do 0.9, et cetera. And we finally decided on doing the COCO AP, which was, let's just do them all. So we basically measure, what percentage of data can you get at 0.5, 0.7, and 0.9, all the way up. I think we went from 0.5 to 0.95 IOU, because basically after 0.95 IOU, you're basically 100% correct or within the margin of error of the segmentation anyway. So, this allowed us to watch the field and progress, even as algorithms got better and better. But this again was another discussion that went on for quite a while. So evaluation. So evaluation limits research. Let's look at this. So before 2005, and before the current, the last 15 years, emphasis on data sets, the way that you would write a paper was you'd first kind of think about, object recognition in the abstract, and you kind of think to yourself, what's an interesting algorithm? And you come up with a cool algorithm, and then you'd find a bunch of images that it worked on, or a bunch of categories it worked on. So basically, whenever you wrote a paper, you had two tasks. One was write an algorithm, and then next was find images that it worked on. And they were pretty much equivalent. And then you would try to publish the paper. After 2008, it would kind of turned into the opposite, because it was kind of the age of data sets. When data started getting larger, it became like a recognized practice to always, evaluate on known data sets. So there, generally what you do is you kind of pick a problem by picking a data set, and then you find an algorithm that works on it. And what you saw here was that data sets and algorithms were no longer, equal partners anymore like they were before. And what they were is would basically have a data set kind of leading the way, and then the algorithms basically had to follow it. And as I mentioned before, this becomes an even bigger issue, when you have a data set like Caltech 101 or 256, which had a small number of training examples, and the hand-coded features, weren't making people happy. So not only did we need to, create a challenging data set, but it had to be a really large data set, because, this is the age of deep learning. So everything had to be done bigger. So what's the consequence? Well, large data sets means they're generally expensive. You're spending $100,000 or more on Mechanical Turk to build these data sets, and a lot of them significantly more than that. Expensive means it's hard to create a lot of them because, well, they're expensive. You're not gonna spend money on just creating random data sets here and there. And then if something's scarce, it's valuable. And what I mean, it's not just valuable as in like that's the amount of money you spend on the data set. What I mean is valuable in that it's valuable if you do well. Since there's only a small number of like large, like kind of well-respected data sets, then if you write a paper with an algorithm that does really well in the data set, it's going to get noticed. It becomes valuable within the community. It becomes what people like search for, what they're looking at. when looking at the best papers within a conference such as ECCV. And then this leads to this, which is basically everybody kind of following each other. You know, there's so many similar papers out there, so many kind of, we call them like algorithm plus papers, where you just kind of, you know, searching for the next best number. You just want to beat state of the art. A lot of times, you know, there's not something incredibly novel or unique in the algorithm, but it does perform better. And those are the papers that get accepted. So let's finally talk about the streetlight effect, which is what I named this talk after and what I mean by this. So if we look at this cartoon, let me just quickly read it. So you have this guy sitting on his hands and knees by the street, you know, on a sidewalk. And he says, you know, I'm looking for my quarter I dropped. And he's telling this to a police officer. And the police officer says, you know, did you drop it here? And the guy says, no, I dropped it 2 blocks down the street. And then the police officer asks, then why are you looking for it here? And he says, you know, the punchline, because the light is better here. And that basically, that sums up a lot of the work that we're doing right now in the field. You know, because, you know, instead of, you know, there's a lot of times, you know, a graduate student comes up and they're like, I want to study this problem, I want to do this. But then you think about the amount of work that you would have to do in order to come up with the right data set, the right evaluation metrics, training, testing data, et cetera, all of that becomes too hard. So they end up kind of shifting their problem to one that kind of fits within the current like data set paradigm, within the data sets that already exist. The problem is that some problems are hard to evaluate, but that doesn't make them less important, even though it does make them less well examined. To put that more eloquently, not everything that can be counted counts, and not everything that counts can be counted. An example, image captioning. This is a cool problem. Is it one that's important? Yeah, you know, it'd be great to have, you know, computer vision algorithms that can, you know, describe an image and, you know, like this, like a giraffe standing in the grass next to a tree. You know, like that'd be great to have that feature. You know, of course it fails sometimes too. Like I heard a giraffe walking down the street in the middle of some trees. You know, it's kind of funny, but it'd be great if these algorithms worked. But at the same time, I've been going around, at least I was, you know, 5 years ago, going around saying, hey, don't study this problem. And why did I say that? The problem is it's so hard to evaluate. It's hard to tell if you're actually making progress or not. So here, what you'll see is 3 different evaluation metrics, cider, meteor, and blue. And every dot corresponds to a different algorithm. And what you'd expect is that as the automatic metrics get better, as a vertical axis, then the human judgment, which is basically humans coming in and saying, hey, are these sentences or captions good or not? That should also increase. So you should see like a nice positive trend here. And what you'll notice is that it's kind of all over the board. There's a little bit of a trend here, but not much. And then you have this kind of crazy outlier over here. Any idea what that is? So these ones are actually human captions. These are ones generated by humans. So what you'll see, interestingly, is that the human captions don't perform as well as measured by the automatic metrics as, you know, algorithms that already exist. Yet by human judgment, they're heads and tails above what these automatic algorithms are generating. So because of this, it's hard to tell whether we're improving or not. And that's a problem. In response to this, and in the middle of the image captioning craze, several of us, David Parikh and Dhruv Batra and their students, we sat down and we're like, you know, this evaluation thing, you know, it's not working for image captioning. It's going to make this problem a hard one to study. Yet we still care about, you know, language and vision. Is there another way that we can pose this problem such that you can evaluate it? And that's how the VQA dataset came about. Was that we wanted a language and vision task that you could evaluate. And since the answers in the VQA problem are so easy, they're like yes, no, blue, white, 1, 2, that sort of thing. They're easy to, you know, they're easy to tell if you got them right or not. You know, it's not as ambiguous as it is evaluating an image caption. So VQA is kind of an interesting data set if you think about it, because it's a data set that was created not necessarily because this was the exact problem we wanted to solve, but it was a problem within the overall family of problems that we wanted to solve that we thought you could evaluate, and therefore you could show progress, you know, from a research perspective. Now, I'm not going to go into today. There's a lot of other kind of interesting follow-up stories on VQA and how bias was an issue and, you know, et cetera, that sort of thing. But it's just, you know, kind of keep that in mind when you're thinking about new problems and thinking about evaluation metrics, and thinking about, you know, why are we studying the problems today that we're studying? You know, is it because it's the only problem that we can evaluate, or is it because it's the problem that actually matters? And speaking about problems that actually matter, so let me talk about the fastMRI project. And this is one that's really interesting from an evaluation standpoint. And this is a collaboration between Facebook and, I think hidden behind my video here is NYU. That's the NYU Radiology Department. Now, what is fastMRI? So fastMRI is a problem where you want to speed up the acquisitions of MRIs. So an MRI is something that's used that kind of scans your body, and you can see soft tissue. It's great for diagnosing a lot of different ailments. It can be used all throughout your body, your brain, knees, feet, you know, abdomen, all sorts of different places. And they give you a wealth of information. The problem, though, is that they can be slow. They can take up to, you know, 20 minutes or to an hour to acquire. And it's really not that fun to be in an MRI because you're in this enclosed space. They're really loud. You have to sit still. Nothing that's really that fun. So a lot of what this means is a lot of patients are too sick to stay still. Children, you know, have to be put under. You have to reduce, you know, if you can't use an MRI, you have to use X-rays or CT, which will increase your, you know, amount of radiation. And, you know, hopefully we can, you know, MRIs are expensive. So you want to increase the number of people that can get MRIs. So if you can make them faster, more people can get them. So the way that MRIs work is you have a scanner, and what it does is it samples the K space or frequency space, think like Fourier domain, and it just kind of scans it, goes along, and that's why it takes so long to capture, because it's kind of scanning one line at a time. And then you do your inverse Fourier transform, and you get your final image out. The hope is that with fastMRIs, you just kind of subsample those lines, and since you're subsampling, you only have to sample a smaller number of them, let's say 1/4, you can then do the scan in 1/4 of the time. So if you do a fully sampled image and you get this, if you do the undersampled and you do an inverse Fourier transform, you get an image that looks like that in the bottom right-hand corner. Not too pretty, not something that a radiologist can look at and then do a diagnosis from. So the hope is that using AI to learn a good prior on what MRIs and needs look like is we get an image that looks like the one that you see there. All right, so I'm not going to go into how to train models, et cetera, that sort of thing, because we're talking about evaluation metrics today. So let me show you 2 examples here. So this is from the challenge that we held at NeurIPS last year. And if you look at these 2 MRIs, one is a ground truth that you see here on the left, and one is an entry from one of the challenge participants. And if you look at both of them, you look at them really closely, especially with any compression that you probably have due to watching this video, you probably can't tell the difference between the 2. And even me looking at both of these here on my monitor, it's hard for me to tell the difference between the 2. But let's zoom in. If you look at the square, do you see any difference? Zoom in further. Now look at just at the end of this little yellow arrow. You see that little clump right there? You see it's in this one, the ground truth image? It's missing here. What that means, that's a subconhedral osteophyte, which is something that radiologists look for. It's a problem. It's something that they need to diagnose. Yet it's only like 3 or 4 pixels big on these MRIs, and the algorithms missed it. If you looked at these 2 images, these 2 images that look like this, and you just did SSIM score, a mean squared error, and you just looked at pixel differences between these 2 images, those differences of those few pixels right here that actually matter to the radiologist, it's not going to be picked up. It's going to be like random noise anywhere else in the image. So you're not going to be able to tell whether your algorithm is doing a good job or not just by using like simple automatic metrics that exist out there in the literature today. And this bears out. If we have radiologists rank these, rank the reconstructed MRIs versus the automatic metrics, we get something similar to what we saw with the image captioning. The axes are kind of flipped a little bit funny here. So you ideally want it along these gray arrows, you know, going from the top left to the bottom right. What you'll see is that certain algorithms perform better by SSIM, but then they do worse as far as the radiologist is concerned. So you get this, you know, you don't get this clear correlation between automatic metrics and what radiologists believe. What does this mean? Well, what this means, if you want your algorithm to actually be used in practice, you need to have them looked at by radiologists. You need to do clinical interchangeability studies. And this is something that we recently did for the fastMRI project. And it's a lot of work. You have to, you know, find a radiologist. You have to do the study correctly. You have to have them look at the ground truth MRI. You have to have them wait a month, and then they can look at the the reconstructed MRI or vice versa. You have to have them do diagnoses to make sure that the diagnoses are the same between them. All of this is very time consuming. It's a lot of work, but it's important. And I think that's something that we need to consider is, a lot of problems, especially if you want to work on real world problems, means that results are going to be delayed. It might not feel as satisfying because you're not going to, be able to hit the button and get a result and publish it in the next conference proceeding. Is you're going to have to wait 6 months. You're going to have to wait 12 months to actually get your results published. And this can be challenging, and it was for me as well because I'm so used to having things done immediately. But still, it was nice when these results finally came out to have them verified and shown that they are correct. So anybody who's working in real world problems and thinking about this, I encourage more people to kind of take this view. So one question I was thinking about and coming up with this talk was, what does it mean to do research without evaluation? Because one thing you might think of is, well, as we were discussing, these evaluation metrics are kind of limiting the type of research we do, because if evaluation is too difficult, or the generating the test set, or the gathering the training data set is too hard, you might just be discouraged from studying the problem altogether. So why don't we just kind of eliminate evaluation? What would that mean? Well, this is kind of how the field worked, before 2000 or 2005. And what you would do is you would come up with an algorithm, such as in 1973, this constellation model. It's really famous. You should read the paper if you haven't already. And it did a great job of recognizing faces like the ones that you see here. You could even do it when you added noise. It's pretty cool. And they showed it working on 16, I believe, individuals, and it was great. And then, here's the example with noise. And then even up to 2003, you had this paper here, which is, kind of revisiting the constellation model. And, this won Best Paper Award. Yet they came up with an algorithm. It's a very compelling algorithm. They showed it worked on this data set that you see here. It has a huge number of citations, won Best Paper Award. But if you look at the paper, does it compare against other state-of-the-art methods? No. It basically, the evaluation was one that they came up with themselves, the data set they came up with themselves. So you might ask yourself, how do you review a paper like this? Like, how do you review papers in which they're proposing a whole new way of evaluating, or a whole new data set of evaluating? Well, it becomes a difficult problem because you're not only evaluating the algorithm, you have to say, well, is this algorithm novel? Is it new? Is it interesting? But you have to look at the results and say, are they compelling? Are they interesting? And there it became, and this was true in stereo vision as well as object recognition or classification, is you kind of, as a reviewer, you had to think to yourself, are these results compelling? Is this something that I think the algorithms that I work on could work on? Because there was no direct comparison typically. You just had to, were the examples hard enough? And you also had to look at the data set carefully, because in this case, yeah, it can recognize faces, but all the faces were taken essentially with the same lighting, frontal face, the same camera. So you had to kind of, you had to look at it and say, like, how hard is this really? Or the motorcycle case, all the motorcycles are facing the same direction, etc. And you had to interpret that and say whether it'd be good or not. And this is fine, especially when not many algorithms are working, or you don't have any good solutions. You want to have a lot of creativity. You want to you want the field to kind of bounce all over the place until it finds something interesting. However, this is good in the beginning, but ultimately it limits the progress in the long run, which is why the field switched, I believe. And it actually led to a lot of progress in the field when we started congealing around certain data sets and certain evaluation metrics. So it was good, as long as we continue showing progress, which, maybe in the longer run, if we start maxing out and, we see plateauing in a lot of data sets that we have, and we don't create new data sets and new evaluation metrics, then it can start being detrimental again. So we have to be careful as a community to make sure that we're always kind of constantly pushing ourselves further and further. All right, one final thought. Don't bury your head in the sand. I think as a graduate student, and many of us, we love thinking about algorithms. We always want to be like, we want to come up with that clever algorithm that solves a problem that everybody's super interested in. We want to get the best results on COCO or ImageNet or, whatever data set it is that you're currently interested in. and you focus on that because algorithms are fun to think about, they're fun to design. However, do you want to be the best player? Do you want to come up with the best algorithm? Or do you want to set the rules of the game? And that's the way that I think about it. If you create your own data set, your own evaluation metrics, you're not just a player, but you're actually setting the rules of the game. You're deciding what people will work on. And if you think about, your research and you think about the impact that it's having, algorithms can have tremendous impact. But, helping people and helping the community to find interesting problems, inspiring people to work on new problems can have equal or even more impact, I think, in the long run. So for, all of you out there that might be thinking about new problems or want to create new data sets, I encourage you to do so. And make sure you take the time and effort to do it correctly, come up with good evaluation metrics, and think about all of the, different problems and all the pitfalls that you might run into, and make sure that you do it thoughtfully in a way that will allow that your data set will be used and productive for, maybe 5 years, 10 years, even longer. So with that, I just want to say thanks and thank you for watching, and have a great ECCV. See you.